All right, you'll need a calculator for today. I know. We're going to talk about graphs and data. This is the beginning of our next unit. We'll have 4 lessons, a kind of review day, then another review day, then our next test. Next test isn't for a while. We have a PSAT day, which we won't have class for, but it'll be all right. So, the experimental design process. Step 1 was ask a question. Step 2, produce the data. Step 3, analyze the data. Step 4, make a conclusion. Conclusion. Okay? We talked about this first day of class. You know, we did an entire experiment, asking all the questions, producing data, analyzing, then concluding. Unit 1, we were kind of about the producing the data. Unit 2 was also about producing data, creating samples. How do we sample a population? And then how do we conduct an experiment to produce the data? Well, Unit 3 through the rest of the year is going to be analyzing the data and concluding. Okay, so we move away from the producing the data part, and we're pretty much done with it. We've talked about how you can conduct experiments to produce data, so we're done. Instead, what we really need to be focused on is analyzing data. Okay, and this could be data of our own experiments or experiments done in from other people, and just being able to look at their data and analyze it correctly. And data is usually helpful if it's visualized, so our first lesson is the different types of visual ways you can look at data. Just to reiterate. Okay? Now, describing data. We say the distribution of a variable tells us what values the variable takes, how often it takes those values, and it shows the pattern of variation. That's just a fancy definition. You don't have to worry about it too much. We should remember from our Unit 1 the 2 types of data we could have, categorical or quantitative. And these are all different ways to show the types of data. Okay? We're going to focus on the bar graph, the pie chart, the segmented bar graph, but really not too much today. We will talk about histogram next class, stem plot next class, and the other graphs in the future classes. Okay, and you don't have to necessarily have all categorical data to be a bar graph. Sometimes there's quantitative data that'll be a bar graph. Quantitative data can be a pie chart. It all depends. Okay. But typically it is a bar graph and a pie chart here, and these are over there. So whatever. First chart we are going to look at. The charts to maybe show this. This is some categorical data. We polled people from 25 to 34 years old in 2000. This is from the census, so this is the entire population. This wasn't from a sample. This is in thousands, so this is 4 million people, 11 million, 10 million, 8 million, 2 million. And this is what is the highest level of education that you received. So we see 4.4 million people in the country from 25 to 34 received less than a high school diploma. 11.5 received a high school diploma. 10.6 received some college, 8.5 graduated from college, and 2.4 received a master's or a doctorate, okay? Giving us our total. Two ways to look at this. We can either turn these whole numbers, these numbers into percentages, and we can use the percentages to create a pie chart. Pie chart is great for percentages that add up to 100. So this is our first example of a chart. Categorical data turned into percentages, quantities, and then we can use a pie chart. We also could have used a bar chart to display this data. Bar chart is a great chart used for totals. So instead of having percentages on the left axis, we would have the totals so that we can see, how many have less than high school, graduated, some college, bachelor's degree, advanced degree. Okay? So pie chart, percentages, bar chart, totals, both for categorical data. Now, I'm going to make sure we are comfortable calculating percentages. A percent, a total out of 100, you take your part, you divide it by your whole. If we don't know that, we know that now. Okay? So what they did in the previous situation, they took their high school graduates, 11.562 million. They divided out of the total amount of people that they put together, 11.562, divided into 37.786 is 30.6%. You would get an answer on your calculator of 0.306, but then you move the decimal place over twice, and that becomes 30.6%. Okay? 11.562 divided by 37.786. Okay? That's how we calculate a percent. Well, we're going to produce a bar chart, and we're going to produce a pie chart for some data that I gathered, okay? Back in the day, before I was a teacher, I was a stock market analyst, and I analyzed certain companies, and one of the companies that I analyzed was GE, okay? Now, who here knows what GE is known for making and what they sell and what they get money for doing? Well, appliances, right? GE makes your dishwashers. GE makes a lot of refrigerators and washing machines, right? Well, it turns out GE is a lot more than just that. That's kind of what they're known for. But what they also make are jet engines, the parts for airplanes, the train cabooses, or whatever you would call them, the big engines for trains. What else do they make? They make power plants. They make turbines to produce energy. They make all of this money. They make stuff that goes into hospitals, diagnostic equipment, like X-ray detectors, different types of machines to testing, MRI machines. They make all this stuff. And here is appliances. Okay, they make appliances. And turns out in 2013, which is the year that I looked up, and this is in millions, they made $8 billion of revenue from selling appliances. Well, let's create a pie chart and a bar chart to see how much that really is compared to all of the revenues they produced in 2013. So what I would like everybody to do is, using their calculators, I would like you to find the percents of the total each of these line items are. And then I'd like us to create a very simple, very sketchy pie chart, and we'd be able to see how appliances, which we know of GE being their main thing, is actually very, very small portion of their business compared to all of the other businesses that they are in, because they're a huge conglomeration. that actually sells most of the big ticket items used in industries. This isn't even all of their revenues. There's actually more revenues that they get from financial management and other services. So I've been talking a lot. What's the first thing I need to do, Mr. Johnson? Good. We got to add them all up and see what the total revenue is. And what is it, Mr. Johnson? It'd be 103,602,000,000. That's how much money they make on a year. $103 billion in revenues. Okay, so that's our total. Let's go ahead and find our percentages. That's cool. Yeah, go ahead and round them to maybe the nearest 1/10 of a percent. It's probably fine. Who got power and water? What is the percent of our total for power and water? Mr. Englander? 23.9. So when we plugged in 24.724 divided by 103, we got 0.239. Okay, 0.2387, we'll round up to 23.9%. Okay, I'm sure oil and gas and energy management is going to be similar to that. Did we find that, Ms. DeVries? Okay, let's find it. Everybody find it. I want to see all of these percentages on our paper. I want you guys to all calculate the percentages. It's just your part divided by your whole. We get a decimal, we convert it into a percentage. Beautiful. That looks good. Perfect. 0.237 around, if we round up, which is about 24% or 23.7%. So almost 50% of their total revenues are from power and water. So power and water, that's hydraulic systems to produce power. Power, they actually make nuclear power plants, all sorts of systems to manage electricity grids. They make it all. Their customers are like energy companies, like Austin Energy will buy stuff from GE to manage things. They don't make it. Then what's next, Miss Mann, for aviation? Yeah, it turns out their largest is aviation and transportation. That is their jet engines that they make that goes into planes, that are other aircraft parts, also engines for trains. Still use trains a lot in this country. What do we get for healthcare, Ms. Loeffler? 17.6. And then Mr. Morris, lonely appliances, how much is that? So we got 0.081, 8.1%. So if we drew a pie chart, it would be fantastic just to show how much we know GE to be and how much it really is. So we got like a 23, we got like another 23, we got another 23. It's almost like 75% is taken up by 3 different items, and then we'll have a lonely little 8.1%, which is appliances. Our largest is aviation and transportation, 26.8. What looks like 26. I don't know if I found one. Maybe this one. We have 23.9 for power and water. Maybe that's this one. Healthcare is 17.6, so that's probably this one right here. These are all your hospital items. And then 23.9 is, oh, sorry. 23.7 is oil and gas and energy. Okay, fascinating. Only 8% of its industrial revenues are from what we know GE to make. A lot of people don't know all the huge items. A lot of companies are out there that you have no idea are out there that make a lot of stuff in this country that we use. Okay, we could also make a bar chart doing the same thing. We would instead, for our bar chart, we would use our totals. Okay, 24, 24, 27, 18, and 8. That'd probably be a better way of using your bar chart. The next slide shows different types of charts used to kind of help display what happened in a certain situation. These charts are all from data from the Titanic. Okay, and this right here is a bar chart showing the total amount of passengers. This amount of men, this amount of women, this amount of children. You could add them up to find the total amount of passengers. Okay, so bar chart totals. This is percent. This is our pie chart. This is our percent. Percent men, percent women, percent children. Same as what can be seen here, it's just in terms of percentages. Finally, we have a segmented bar. Now, sometimes segmented bar can be totals or it could be percentages. This is using percentages. It could be totals. It would look very similar, just I'll show you what it would look like with totals. So this is the percent of children saved versus the ones who lost their lives on the Titanic. This is the percent of women that were saved versus the ones that lost their lives on the Titanic, and this is the percent of men. You can look at the same data here on this bar chart. You can make it a segmented bar. You know that 18% of men lost their lives. This would probably be about 18% or were saved. You'd probably sketch this to be like total amount, the amount saved, the amount who perished. Women, you would probably put this, about 76%. This would be the amount saved, the amount who perished. And then children, 50-50, which is kind of crazy if you think about it, right? You would think all the children would have gotten out first. But I don't know exactly. A lot of the children could have been in the lower levels, and maybe that's the compartments that filled up with water the fastest, and maybe that's what happened. I have no idea. But interesting. So a lot of different charts showing us data from the same event. Definitely helpful. Here's a segmented bar using percentages. They add up to 100. Here's a segmented bar using totals. Questions about any of these? Okay. Now, line graphs. Line graphs typically are used for quantitative data. Let me use yellow. Line graphs good for quantitative data. They help us show change over a time. I pulled up this chart of average retail prices of gasoline over the last 12 years. Okay? And let's see, we want to make sure we have time on the horizontal axis so that we show the change over the time. We want to make sure to connect the points to show the differences in their change over time. And then after we have that, we can look for overall trends, whether things are increasing, decreasing, or just all over the place. And we'll look at just random spikes, either up or downward, or possible seasonal variation. So let's look at the price of gas. Do we see any overall trends over the last 12 years? Is the price of gas going up or the price of gas going down? Ms. Rios, would you say? It's all over the place. Yeah, we have no idea where the price of gas is going in the future because we have no overall trend. It's up, it's down, it's up more, it's back down. So who knows? I can't even say it's steady. Sometimes you will not have an overall pattern with certain things like gasoline. We do have striking deviations. What are some striking deviations that we see? Look at 2008. We see this huge peak followed by a huge trough, which I completely missed. Do you know what happened in 2008? I remember back in the day, it was in 2005. There's a huge spike in the price of gasoline. Okay? That was because Katrina hit the Gulf Coast and knocked out all of these refineries that turned crude oil into gasoline. And then all of a sudden there was less supply out there. Boom, hurricanes increased the price of gas. And in the next couple years, every single hurricane season that started, people would speculate, oh, there's going to be another huge hurricane that's going to come in and destroy more things. And the price would go up. But it turns out that never really happened. And now that pattern, that seasonal pattern, doesn't happen anymore. This right here, this was just due to speculation in the markets. There was a lot of speculation that we were in peak oil theory. Peak oil means, hey, there's only a certain amount of oil in the ground, right? We're not producing more oil. This is over like thousands and thousands of years of these fossils and this like plant matter being decomposed and turned into oil. However, our population of our world continues to grow. So if we're not increasing supply, but we are increasing demand, shouldn't just the price of oil go way, way up? Well, yes, that is true, and that's kind of what people were thinking. However, that's a very long-term perspective on things. And what people realize is that in the near term, it's easy to increase the production of oil. You can dig deeper in the oceans to find different oil patches that people haven't gotten yet. So this is like deep water ocean drilling. There are different places where oil is hard to get. There's places in Canada where there's oil seeped into the sand. And if you dig up the sand and kind of refine the sand, you will produce oil. Very expensive to do, but if you can make money off of it, you can do it. So all of a sudden it's like, well, actually we can produce more oil in the near term. So this is why this went down. It's another reason why the price of gas, when you guys first started driving, which is right around here, all of a sudden went way down to where it is now, because there's been more oil production in the near term that has increased more than the demand of the oil, which is why our prices are low. Okay, so economics is more than statistics, but economics uses a lot of statistics. Okay, so let's, what else we can do with line graphs is we can look at percentage changes. Percentage changes are very important to do because we like to see overall like how much things have changed, but it's good to compare against other changes if we turn it into a percent change. So percent change allows us to compare multiple quantitative data. So I can compare the amount that gasoline prices has dropped to maybe the amount of car price increases. Maybe car manufacturers are increasing their prices of their cars because they know that people have more money in their pockets to spend on cars because they're spending less on gas. You know, it's certain things you're not going to say, oh, gas has increased 40 cents, but car prices have increased $5,000. That's not very comparable, but if we talk about percentage changes, all of a sudden they become comparable. Here's how we calculate percentage change. 3 ways. You can find the total change and divide it by your original amount. Sometimes the original amount is like your future amount. Or you can calculate your total change by taking your new amount divided by your original amount. Original is not future, sorry. That's a past amount. The new is like your future. You can take your future amount and subtract your past amount and divide that by your past amount. Or if you do a little bit of algebraic manipulation, you can take your new value, divide it by your original value, and subtract 1. And this is how you find percentage change. And this is what I use whenever I'm doing my calculations. New divided by original minus 1. And it's the same as this. It's just original divided into new minus original divided by original. Let me show you an example. In September of last year, the price of gas was about $3.60. This year, it looks to be about $2.34. So the year-over-year price from 2014 to 2015 in September, change would be the new price, $2.34, divided by the original price, so last year, which is $3.60, minus 1. If I calculate that using Mr. Englander's calculator, I get 234 divided by 360 minus 1, negative 0.35, a decrease of 35%. Which makes sense. Higher value to a lower value, we declined in our price. How much? By 35% of our original value. Okay? You guys are going to do some calculations. That way I know you can do this. The average price of gasoline is $2.34 today. At the beginning of the year is $2.09. What is the percentage change from the beginning of the year to now? Compare your answers with a neighbor once you get it. Make sure we're all on the same page. Calculate it and compare, please. Everybody, make sure we can do these calculations. Your new value divided by your original value minus 1. That's okay. I got it. Cool. Perfect. Excellent. We should get 11.9 or 12%. I got 2.34, which is today's, our new price. Our original price was 2.09. I subtract 1. I get 0.119. There is an increase of 11.9% in gas prices so far this year. You could have also have done 2.34 minus 2.09 divided by 2.09. It's the same calculations. This is just algebraically different. Just looks different. Okay, another one. What is the percent change from the high point in the last 10 years till today? I bought my car when gas was around here. So I bought a very small fuel-efficient car, figuring out that, assuming that gas prices are going to stay the same. I should have known better, knowing that gas prices change a lot, and I didn't have to buy a super fuel-efficient small car. But I like my fuel-efficient small car, so I'm not complaining. But it looks like the high point was $4.10 in July of 2008. I bet you a lot of you guys are buying very expensive trucks because you see fuel prices down here. And maybe after looking at this chart, you shouldn't feel great about that decision if things change. But who knows? The prices could go down even more. How much? Go. Get your answer. Compare it with your neighbor. This would be a decrease from $4.10 to $2.34, but as a percentage basis, how much did it decrease?
I don't understand, how to find what percentage change. Is it for one of these equations?
Yeah, I use this equation. You can use any of these equations. It's the same.
Okay.
Okay. I use this one just because I think it's easy to plug into a calculator.
Yes.
Take your new, you divide it by your original, and then you subtract 1.
Okay.
Just like you did.
And then that was what we do for number 2?
Yep, same thing. We want to find the percent change. You found the percent change between the beginning of the year and today.
Oh.
It was 11.9% increase.
Okay.
Okay. Let's find the percent change from the high point in the last 10 years to today. So from $4.10 to $2.34.
Okay.
Okay. Move it over twice. That was your original price. Think about the past versus the future. Let's go back to that. If new and original confuses you, think about the past and the future. This is the future. This is the past. Or this is the present and this is the past. So which number goes in the numerator? Which number goes up top? Is it going to be the 410 or the 234? Is that the future cost and the present cost? Which one goes on the top? The 234, your present value or your future value. Then the past goes on the bottom, 410, and then we subtract 1. This will give us a negative number, and when you see a negative number, you should feel confident in your answer because we know we went from a bigger value to a smaller value. And the number is what? Mr. Johnson? Yes, negative 43% or 43% decline. All right. What is the percent change from the low point in the last 10 years till today? Looks like $1.59 was the low in January of 2009. So funny how we went from such a high price of gas to such a low price of gas in such a short period of time. Commodity changes. They're crazy. A lot of people were investing a lot of their money in gold, thinking that gold was a very, very safe place to put their money. But gold prices have gone way down. And all that investments have decreased in value. Something that usually doesn't decrease in value. Can anybody think about some commodity that does not decrease in value? I feel like I'm an economics teacher. Maybe food? Let's see, food. Well, depending on the seasonality, you can produce more food. You can plant more wheat and produce more food. It's true. They do stay consistent, but they could go up or down. I mean, if you were in Russia, depending on the year, all right, well, there you go. Those are commodity prices. Usually you need to have a very, it needs to be a very restricted commodity where you can't change the amount of supply or demand. So I would say like land. Land is something that will just continue to increase because there's no more land being created. All right, so what do we get? 38% increase. 47% increase. It should be a positive number. 234, which is our present value, should be over our old value of 159, and that is what is it? 20. Oh, okay, cool. We are 43% off the high of the last 10 years and 47% above the low of the last 10 years. Okay, so that's percentage change. You can do line graphs to look at change of quantitative data over a long period of time. Here are some examples of seasonal graphs, graphs that show seasonality. This is Southwest revenues, Southwest Airlines revenues. You can read that. Okay. What it shows is that we're doing this by quarters. So quarters means like first quarter is January, February, March. Second quarter is April, May, June. July, August, September, October, November, December. January, February, March, April, May, June, July, August, September, October, November, December. What you'll notice is that January, February, March, people don't fly much. But then April, May, June, your spring break months, your beginning of vacation months, people fly a lot. Okay? And though you see an overall increase in revenues for Southwest, there are these consistent bumps patterns that go along, where you go from a low point of January, February, March, where people do not fly at the beginning of the year. They're just starting their new years of their work, of work. They're not flying much, but boom, April, May, June, you have spring breaks, you have beginning of summer vacations, they fly a lot, okay? And that is kind of consistent. January, February, March, April, May, June. January, February, March, April, May, June. January, February, March, April, May, June. This is called seasonality, where depending on, the time of the year, you will have more revenues, more customers, more whatever for your business. Great. Another example would be like to plot out ice cream sales for some ice cream store, like a Cold Stone Creamery. You're probably going to see much higher revenues in the summer than you will when it's colder. Okay, that's what it means to be seasonality, and you can see seasonality within the graphs. Here is another example of timber production. You can see this is a great example of seasonality, which in each year there are increases and decreases because of the weather that will help you or hurt you when you are producing timber. This is consistent variations, which is seasonality. Does that make sense? Any questions about seasonality? All right, moving on to bad graphs. We need to make sure that our graphs are scaled so that people understand what they're looking at. If you look at this graph and this graph, without looking at what they're doing, you see a bigger change between 2002 and 2004 here than you do here. Nod your heads. Yes, that's correct. Right, Ms. Pushman? Nod your head. Okay? However, this is the same exact data. Same data showing different results because of this axis. This is from, maybe 8 to 10 to 12. This is starting from 0 going to 12. It is the same data. So we need to be aware when we're looking at graphs, whether in the news or on TV or whatever, of the axis that you have, and make sure that you know where the axis is, because we can see huge differences when there might not be much. Here's another example. I see a huge difference between this poll of Democrats and the poll of Republicans for whatever this question is. Okay, huge difference. However, we notice we start at 53 and go to 62. Instead, if we looked at 0 to 100, there's not that big of a difference. So CNN, that produced this, was very misleading in the way they represented this data. Hugely misleading. And this is a, reputable news company. However, they like to produce things that look crazy and shocking to get people to continue to watch them and go online, instead of something that's like, well, they're about the same. 62% versus 54%. It's not very far off. Here's another example of how we could stretch things to make them look different. This is the same exact data about the amount of unmarried couples over the course of 20 years, from like 78 to 98. And we see, yes, there is a steady rise. However, you looked at the same data and you just took this y-axis and you stretched it up. And if you took the x-axis and you stretched it in, then all of a sudden, what was just a steady increase becomes a huge increase. So we need to be careful about how we are stretching our data. And this is where it's helpful to look at percent changes. If we looked at the percent change between here and here, we'd have a good idea of what the true increase is. And it would be the same for this as this. We need to make sure we're using the correct type of graph. If we are trying to pick a graph to display that we can send to a journalist who's reporting on crime rates. Here, this is crimes per 1,000 citizens. We can see as the years increase, there's less crime. However, this is very confusing because you got years on the y-axis and you have crimes on the x-axis. So if you look at it the wrong way, it's almost like the crimes are increasing. Whereas if we had a line graph, the correct chart for a quantitative data over the course of time, we can see, oh, the crime rate is decreasing over the years. So make sure we pick the correct graph to display our data. Pictorial graphs are kind of confusing. They are misleading because typically the size of the picture does not correspond with the difference in, say, sales or whatever our data is. It may appear to be a greater increase than it really is. Example of this looks to be just a little less than twice the size of this. But however, if you look at the size of this pen, the total area of this pen is probably like 4 times the area of this pen, which is a little bit confusing. Same with this. The area of the skim milk carton looks to be more than twice the area of this one. And since this has a different width of this bar compared to this, you might be confused. However, if you kept the widths of your pictures kind of the same, and maybe you stack the pictures, that would be better. So we need to be careful with this. We keep the widths the same with pictures. Okay. When we're using categorical data that is produced and putting into a bar chart or a pie chart, we want to make sure of what if we're using percentages. What could be wrong when we look at this one? Doesn't add up to 100. Okay, if we're using percentages, we probably want to see all of the results because it's like loud music is 18%, but maybe there's something else that is like even higher than that that they're not showing. I don't know. Here's another great example of a bad chart, a bad visual data representation. Here they kind of use a pie chart. Look at this graph and talk with your neighbor about what you think is wrong with this chart. Right, so you look at McDonald's and it's like, man, McDonald's has like over half of the market. But no, it only has 15.8% of the market share. So if you look at the differences between the market share of Burger King and McDonald's, and you're like, oh my goodness, McDonald's has so much more. But you know, these data points, they don't add up to 100%. So there's a lot of other things that are going in between the Burger King and the McDonald's. And all of a sudden, the difference should not seem that great. It is pretty large, but not this large. This is not 51%, it's 15.8. And this is not like, looks like 24%, it ends up being 6. So we don't like this graph because it's not adding up to 100. Ways that graphs can be manipulated. In summary, we could change our axis, we can stretch things, scale things. We could crop to focus on desirable information. That's if we change our axis to not start at 0 and to start at just the value right before or right after. Certain things with three-dimensional effects, that's our pictorial graphs where we could have volumes looking to be much, much larger than the differences that they actually are. That's kind of similar to the pictorial embellishments, and we could have some mathematical areas. Example, that pie graph where just the stuff doesn't add up to 100, and yet you have an entire burger making me believe that you have 100%. Okay? Categorical data goes into bar and pie. Quantitative data typically goes into a line graph. All graphs need, you know, the basic stuff that you need: a title, your labels, your legend, an accurate scaling. Make sure it's easy to read. And that's it. That's the lesson. It's very simple. Okay? Some percent change, some percent of calculations, and then some charts that you're already familiar with. Good. Next class, we're going to be talking about, you know, histograms, medians, quartiles, stuff like that. So possibly new stuff for a lot of you. So be prepared for that.